So these two methods always work for moving exponents. So the next thing that I'd like to do is another fairly tricky example. And this one is not, strictly speaking, within calculus, although we're going to use the tools that we've just described to carry it out. In fact, it will use some calculus in the very end. All right? And what I'm going to do is I'm going to evaluate the limit as n goes to infinity of 1 plus 1 over n to the power n. So now, the reason why I want to discuss this is it turns out to have a very interesting answer, and it's a problem that you can approach exactly by this method. And the reason is that it has a moving exponent. The exponent n here is changing. And so if you want to keep track of that, a good way to do that is to use logarithms. So in order to figure out this limit, what we're going to do is we'll take the log of it and figure out what the limit of the log is instead of the log of the limit. Those will be the same thing. So we're going to take the natural log of this quantity here, and that's n log 1 plus 1 over n. And now I'm going to rewrite this in a form which will make it more recognizable. So what I'd like to do is I'm going to write n, or maybe I should say it this way, delta x is equal to 1 over n. All right? So if n is going to infinity, then this delta x is going to be going to 0. So this is more familiar territory for us in this class anyway. So let's rewrite it. So here we have 1 over delta x, and then that is multiplied by log of 1 plus delta x. All right, so n is the reciprocal of delta x. Now I want to change this in a very, very minor way. I'm going to subtract 0 from it. So that's the same thing. So what I'm going to do is I'm going to subtract log of 1 from it. That's just equal to 0. Right? So this is not a problem. And I'll put some parentheses around this. All right, now you're supposed to recognize all of a sudden what pattern this fits into. This is the thing which we need to calculate in order to calculate the derivative of the log function. Okay, so this is, in the limit, as delta x goes to 0, equal to the derivative of log x, where, well, the base point is x equals 1. That's where we're evaluating it. That's the x0. That's the base value. So this is the difference quotient. That's exactly what it is. And so this, by definition, tends to this limit here. But we know what the derivative of the log function is. The derivative of the log function is 1 over x. So this limit is 1. Okay, so we got it. We got the limit, and now we just have to work backwards to figure out what this limit that we've got over here is. So let's do that. So let's see here. The log approached 1. So the limit as n goes to infinity of 1 plus 1 over n to the n, so sorry, the log of this, yeah, let's write it this way. So this is the same thing as, well, the thing that we know is the log of this, right? 1 plus 1 over n to the n. N goes to infinity. That's the one that we just figured out. But now this thing is the exponential of that. So it's really e to this power. here. So this guy is the same as the limit of the log of the limit of this thing, which is the same as the log of the limit. The limit of the log and the log of the limit are the same. Log lim equals lim log. Okay, so I take the logarithm, I take the exponential. That just undoes what I did before. And so this limit is just 1. So this is e to the 1. And so this limit that we want here is equal to e. So I claim that with this step, we've actually closed the loop finally, because we have an honest numerical way to calculate e. First, there are many such, but this one is a perfectly honest numerical way to calculate e. We had this e, we didn't know exactly what it was. It was this m of e, there was m of a, the logarithm, and so on. We have all that stuff, but we really didn't need to nail down what this number e is. And this is telling us, if you take, for example, 1 plus 1 over 100 to the 100th power, that's going to be a very good, perfectly decent, anyway, approximation to e. So this is a numerical approximation, which is all we can ever do with this kind of irrational number. And so that closes the loop, and we now have a coherent family of functions which are actually well defined and for which we have practical methods to calculate.